Okay, so let's start with RL parallel circuits here. This comes out of Unit 19 of Delmars. There's a lot of similarities between RL series and RL parallel, a few differences. One of them here is how we're going to deal with R2. So I'll give you the value for R1, 15 ohms. R2, I'll give you the inductance, and we'll solve for the resistance. So when we did the series, we had the inductance of the coil is XL over 2 pi f. So, and then what we'll do is we'll just invert this formula a little bit, and we end up with XL equals L times 2 pi f, which means we will take the inductance and we'll end up with 20 ohms. So just to note that unless we carry over many decimals, we're not going to end up with a perfect number like 20. So if we take this, you multiply it, you'll end up with 20.00 yada yada yada. So when we do these exercises, this resistor is going to, the first couple decimal places will be zeros, and that's what we'll use. It'll just be, we'll just use a clean number for these exercises. So in this case, 20.00, we're just going to use 20. So 15 ohms, 20 ohms for these resistors. Now with parallel, each one of them is seeing 240 volts. So the current through the resistor and the current through the inductor here, so E over R, so ET over R, which is the resistor, gives us 16 amps through this line. Current through the inductor, ET, again 240 volts through the inductor, is going to give us 12 amps. So now when we deal with just the straight, so the kind of formula we're using here, C equals the square root of A squared plus B squared. So in this case, IT equals the square root of I through the resistor squared plus I through the inductor squared. And if we just plug those numbers in, we end up with 20 amps at an angle of 36.8 degrees. Now this, depending on how you punch this all in, 36.8 is the angle, but technically this is negative 36.8 degrees since we're sitting on the below the x-axis here. So 36.8 degrees, but negative 36.8 degrees is, and you'll see that when you punch these into your calculators. When we deal with this in polar, we'll see that, so if we take these values, 16 amps angle 0 plus 12 amps angle negative 90. So we're not going to use 90 degrees anymore as we did with series. With these we're going to use an angle of negative 90. Gives us 20 amps at an angle of negative 36.8 degrees. And you'll see that when you punch that into your calculator. So it's 36.8 technically, but as far as the actual position is concerned, we're sitting at a negative 36.8 degrees. So if we continue now, this is a bit, when you read the unit, it skips past quite a bit here. So I've just given you a bit of an inversion here as to how we ended up to this point. There's a little more to it. I sort of trimmed it down a little, but this sort of should give you the idea. So if we take RT, we'll just call it Z, equals 1 over R1 plus 1 over R2 plus 1 over 3, yada yada. I just picked two resistors here. If we invert this formula, we can get to this. 1 over, if we just did some canceling, we end up with this. And then if we carried on through and we got rid of the Z, and we would have to divide this by Z, divide by Z, we end up with 1 over R1 plus 1 over R2 over Z. And then in the book, what you're looking at here is so I've just changed it to XL here. Just same formula, just representing it a little different as it is in the book here. So it's just, yeah, just a little Just a little explanation there for you. So what we have is this formula here, what they show in the book. Now, Z, if we just keep going down this line here, Z is equal to 1 over the square root of 1 over r squared plus 1 over xl squared. And if we just plop the numbers in here, we end up with a total resistance of 12 ohms. So we have ET to finish off is simply IT times RT in this case, and it's 20 amps, and 20 amps times 12 ohms gives us 240 volts. Now, just to mention that right here we have the x-axis, right? We have the x here, we have the y here. Our voltage being common to the two, so we had, for the series circuit, our current was set at angle 0. But with our parallel, we are setting our voltage at angle 0 here. So we have ET, 20 amps, 12 ohms gives us 240 volts. So if we progress now, we want to track down our volt amps. So if we go ET times IT, gives us 240 volts, 20 amps, gives us 4800 volt amps. Our true power, watts, so the E through the resistor times the current through the resistor, so we got 240 volts times 16 gives us 3840 watts. Our reactive power, our VARs through our inductor, gives us the E through the inductor times the I through the inductor, gives us 240 volts times 12 amps, 2880 VARs. And if we express this in the formula here, so we got the volt amps, the total volt amps, 4800, we can do ET times IT. But using the formula volt amps, we got the square root of P squared plus VARs squared. And our volt amps is equal to, so we got 3840 watts right here, 2880 VARs right there. We add that up, knock them down, and we're looking at 4800 volt amps. And if we punch that in, and we do our polar, we got 3840 at angle 0 plus 2880, angle negative 90. It's always important to remember that negative value. 4800 volt amps at an angle of negative 36.8 degrees. And remember, no matter what numbers we use here, this degree will always be the same. So when you have a different angle that comes up, something has gone wrong. That's an indicator that you should be just something to be looking out for to double check your work. And then to finish it off, we have the power factor. And the power factor being adjacent over hypotenuse, the P over the VA, 3840 over 4880 gives us an 80% power factor. And that's it for RL circuits.